Hey everybody, welcome back to the instructional video. This week we're going to be speaking briefly on power and types of error, but for the most part this video will focus on how to test for normality in SPSS. So go ahead and click on Lab Assignment 7, download that and open it up, as well as download the SPSS data for this week and open that up in our program. So pause this and resume when you've done those things. Alright, so real quick, before we go into the SPSS portion, Lab Assignment 7 is pretty short. We have four kind of short description, explanation type questions involving power and error and homogeneity of variance, but the majority of Lab 7 is going to be in SPSS. That's a pretty lengthy one. So let's get started on that one now. You should have already opened up this file in SPSS, so go to that now. What we're going to be doing is working with a data set that has to do with money you spend every month. So what this is a collection of let's see how many people there are in this data set. It looks like about 100. So we're taking 100 people and measuring how much they spend on housing every month. So these numbers here represent the amount in dollars that people are spending on housing. Over here, this is the amount of money they're spending on utilities, and that involves electricity, internet, water, power and heating, etc. The next column is how much they spend on their car per month. So different people spend on maintenance or insurance per month. So it just or gas. So it just is a total number of how much each person spends in dollars on their car per month. The next category is the gender of each person. So participant number 1 is a male, participant number 2 is male, and looks like the first 50 people are male, but then the next 50 people are female too. So it's an even split between males and females in this category. Also in the next category is each participant's ethnicity. And then finally, the last column is their age in years. So if we look at the data set really quickly in variable view, we can tell that I've labeled these for you. The first one is a scale variable, housing. It's in dollars. That means you could spend $0 on your housing. It means you don't have a rent or you might be homeless. So in this case, it would be a scale ratio variable. Same thing for utilities. You might spend $0 on your utilities every month. Same thing with car. You may not have a car, so you spend $0. All three of these variables are ratio. And because all three of housing, utilities, and car are ratio variables, that means that there are no categories to have. It all has to do with numbers. However, if you notice for gender, those are categorical variables, or we can call them nominal variables. So gender and ethnicity are both nominal variables, and that's why they're listed here as nominal. If you go to the labeling for gender, 1 is equal to male and 2 is equal to female, and I set those automatically like we did last time. Also for ethnicity, there are 6 ethnicities. We have 1 is African American, 2 is Caucasian, 3 is Asian, 4 is Latino, 5 is Middle Eastern, and 6 is Pacific Islander. So these are all categories that I measured in this data set, and I wanted to set certain numbers for these categories so SPSS is able to read them. Finally, age is not measured in categories. We don't have age categories over here, as you can see in the data, between 0 and 21 or 22 to 24. These are all just the person's age. So there's no categories here. So that means that the age variable is a scale variable. We're just measuring the actual number that a person's age is. So now that we've gone over the variables and we've also seen what the data is, I want to do a few things that are going to measure descriptive statistics for this data set. It's a really big portion of this class to really understand the descriptive statistics, because once you understand that, then you can get to the fun stuff. But until we understand it 100%, you have to master it. And we haven't done everything in descriptive statistics yet. We've gotten to the point where you should feel pretty good about taking the mean, the median, and the mode, or the standard deviation, or even the finding the outliers in a data set, but that's not everything in descriptive statistics. In order to get descriptive statistics, we need to briefly learn first about some new concepts that we're going to analyze in SPSS. So for the time being, we're going to switch modes into sort of learning the concepts, then we're going to get the numbers. So first off, I want to let you know about quartiles. Quartiles are another measurement of where the data is, where it kind of falls in terms of percentages. Quartiles divide a rank-ordered data set into 4 equal parts, meaning there's some sort of order to the data that you have, and if there's an order, then you can split it into 4 equal pieces. 25% in the first piece, 25% in the second piece, etc., as you see here. So the values that you divide, each part is called the first, the second, or the third quartile. So your lowest value is here, and then there's 25% of your data up to this point, which is called Q1. So Q1 is the point where your first 25% of your numbers ends. And then the second chunk of 25% goes all the way up to Q2. And so Q2 right here is always your median value. It's the middle number. The third 25% is Q3. So at Q3 is your third number that is divided across all these data points evenly. And then from Q3 up to your highest number is the last 25%. So if you're confused at this concept, just know that if I took a bunch of information and I split it evenly between 25% and split into 4 pieces, that's what we're measuring when we're doing quartiles. So here's an example. If you have the following data arranged from least to greatest, now that's something that we do frequently in descriptive statistics. So if I had all this data and I ordered it from least to greatest, this is what it would look like, with the smallest being over here and then going up all the way to the largest value. Once I have any data arranged from least to greatest, I need to find the median. And so that number is the middle of all numbers from least to greatest. So finding the middle number is actually something you should be able to do. So if I count 1, 2, 3, 4, 5, 6, 7, and I count another 1, 2, 3, 4, 5, 6, 7, you can see that the number left over in the middle, in the exact middle, is the median, and that's 14.6. Cool? So right there at 14.6, we can tell that that number is the median value. And it's also the value we label as Q2. So like I said before, Q2 is right in the middle of the data set, which means it's also the median. So we know that this number right here is Q2, 14.6. So if we use that logic, we can divide the numbers into 4 equal parts, 4 equal quartiles. And we should label Q1 and Q3 in the correct spots. So you might be asking yourself, how do I find Q1 and Q3? Well, remember, we need to split these numbers here into 4 equal pieces. So if I have all this data here, I can find Q1 at 14.4. You might be asking yourself how I got that information. How do I know that that is Q1? Well, if you look at the data now, you can see that 14.4 as Q1, there's 1, 2, 3, and then 4. That's Q1 right here. Then we have 1, 2, 3, 4. That's Q2. So using that pattern, where would Q3 be? Well, it would be 1, 2, 3, 4 would be where Q3 is. I'm going to write that in purple. So right off the bat, you can look and see that, oh, cool, we've split the data into 4 equal parts. 1, 2, 3, 4. This whole area is the first 25%. 1, 2, 3, 4. That's the second 25%. 1, 2, 3, 4. That's the third 25%. And finally, the last remaining ones are 1, 2, 3. Because there's an uneven amount of numbers, the last portion is going to be slightly smaller. But they're split into increments of 25%. 25%, 25%, 25%, and then the remaining 25%. So now, if we do that, we've split things into quartiles. And that allows us to do a few more things once we have these put into 25% chunks. We know that 14.4 is Q1. So what I'm going to do here is right under that, I'm going to write Q1, so you know which one that is. Under the next one, I'm going to write Q2, because we need to know what that is. And also under here, we're going to write Q3, so we know what that number is. Alright, so now that we have all the numbers placed in order, we know where the quartiles are, we know where Q1, Q2, and Q3 are, those little points where the quartiles end. You can now find something called the interquartile range, which we'll label as IQR. What this is sort of a measure of variability, and you know that variability means how spread out the scores are. So based on how we divided things into quartiles, the interquartile range is the middle 50%. So it's from the end of quartile 1 to the end of quartile 3. So that tells me that it's sort of like a span or a spread. It tells you what's the middle 50%. Usually we're interested in finding the middle 68%, dealing with standard deviations. Quartiles are just a different measurement. Neither one is right or wrong. This one is just, instead of measuring 34% up above the mean and 34% below the mean, we're measuring now 25% above the median and 25% below the median. So this range, this interquartile range, can be taken and you can actually get a number for how spread out it is by taking Q3, whatever number we got before, minus Q1. So we can actually figure out what that interquartile range is by taking Q3 minus Q1. Well, what was Q3 and Q1? Well, we know that Q3 was 14.9, and we know that Q1 was 14.4. So recall those numbers, because that's what we're going to use to find the interquartile range. So for the interquartile range, we're going to take 14.9, which was Q1, minus 14.4. And that range comes out to 0.5. So that tells me that the interquartile range is just a measly 0.5. But that makes sense with the data, because we were just using, 14.4, 14.6. It wasn't that very spread out. So an interquartile range of 0.5 makes sense. It only differs from person to person by about 0.5. Okay, so the reason that we figured out this interquartile range is, number one, to get a different measure of variability than we're used to, and variance. But it also can be used by a lot of statisticians to find where outliers are. So the interquartile range can be used to figure out what is a possible outlier and what are normal numbers in your data. So a lot of statisticians use the interquartile range in order to find outliers, and they argue that any data point that is 1.5 times above or below your interquartile range is an outlier. That number has been determined over many years by many statistics professors and experts, and it is simply something that is believed to be a better estimate than, say, 3 standard deviations from the mean. So neither is, like I said, right or wrong. There are just different arguments for using interquartile range versus standard deviations to find outliers. Either way, in order to solve what a outlier is using interquartile range, we use the following formula. So any low outlier is the value Q1 minus 1.5 times the interquartile range. So using this data set, what we can do is find what the number for outlier that's really, really low could be. So what was Q1? Well, we took Q1 right here. It was 14.4. So for this first formula, for any low outlier, we would use Q1, which is 14.4, and we would subtract 1.5 times our interquartile range, which was 0.05. I'm sorry, just 0.5. So it'd be times 0.5. Alright, so if you do your calculators, I will bring that up on the screen here. Oh, I have a number up there. You may be that may be what we're looking for. 1.5 times 0.5 is 0.75. This number right here is 0.75. So we're going to subtract that from 14.4. So 14.4 minus 0.75. And when you do that, you get 13.65. So that tells me in this data set, an outlier would be 13.65, a low outlier at that. And that's just one new measurement of what an outlier could possibly be based on interquartile ranges. Well, now, with any high outlier, it's a little bit different. We want to know what's above Q3, which is right here in our quartiles. So we want to know what a possible high outlier would be. Well, we're going to add 1.5 times the interquartile range, and that's going to be what we might consider a very high positive outlier. So Q3, let's start with that. Q3 was the value we found before, which was 14.9. So we'll take 14.9, and we're going to add this time 1.5 times, what was the interquartile range? It's the same as last time, 0.5. So when you do the math, you know that 1.5 times 0.5 is 0.75, but we're going to add that to 14.9. So let's take that number and add it to 14.9. And you end up with 15.65. So any number that is 15.65 or above would be considered a high outlier using the interquartile ranges. Well, let's look at our data set really quickly. Keep in mind 13.65 and 15.65 as our cutoffs for outliers. Keep those in mind. Now here was our original data. Do you notice any numbers under 13.65? I certainly do, 10.2. So that, using our interquartile range criteria for an outlier, this would be considered a possible outlier because it's under 13.65 as our low outliers would be considered. So I'm going to put a star next to that. Anything above 15.65, as you can see, these two numbers are above 15.65, which was our cutoff for a high outlier. So I'm going to put a star next to these values just to tell me that these are possible outliers. Now you may be curious to know if we use standard deviations as we have in the past to see what an outlier would be. It may be different than these numbers. As a matter of fact, you may find that 10.2 is still an outlier, a low outlier, using standard deviations. It lies maybe 3 standard deviations from the mean. But you may find that only 16.4 is 3 standard deviations from the mean. So using standard deviations, you may find different sets of outliers. But what these two methods for finding outliers do is tell you a rough estimate of which scores are just too high. It doesn't tell you exactly what an outlier is, just like the mean, median, and mode don't tell you exactly what the middle is, but it gives you a good estimation, and more ways to find the outliers and find the middle, the better, in my opinion. Okay, so now that we've talked about quartiles, what I want to go over is how to interpret those in terms of descriptive statistics. So we're going to go back to SPSS for the time being. So pause this video and go back to SPSS, and we'll learn how to find some of this information automatically. Alright, here we are back in SPSS, and we're going to find a lot of descriptive statistics in this pretty large data set, but it's going to be nice and easy because up to this point you know how to find descriptive statistics automatically. So go to Analyze in your SPSS file and go to Descriptive Statistics, and finally go to Frequencies. So you'll notice that I have put housing, utilities, car, and age over in the variables category. You won't see that. You'll see it probably like this. So what I want you to do is put housing, utilities, car, and age over in the variables box by clicking this arrow here. The reason we're not doing gender and ethnicity is because you can't take descriptive statistics on those two. I always find it funny to ask the question, what is the mean, median, and mode of gender? Well, it's somewhere between male and female, so you can't really get a number for that. Same thing with ethnicity. What is the mean, median, and mode of African American, Caucasian, Latino? It's nothing, because there is no middle value for those things. They're just groups. So we're only going to find the descriptive statistics for scale variables. All of these are ratio, so they're perfect because they deal with numbers, and we want to find the mean, median, and mode, standard deviation, and variance. But we also want to find a little bit more information, specifically with quartiles, percentiles, outliers, etc. So go to Statistics. Once you've put these four variable names over here, click on Statistics. And I want you to click on Quartiles. I want you to check that box for quartiles, because then it's going to find quartiles for us. It's going to split things into 4 equal groups, each with 25% of the data in it. There's also a button down here that you will not have checked called percentiles. Click on that button, and what I want you to do is I want you to click, you'll have nothing in this box when you do it. So what I want you to do is click on this button and type in 10, and I want you to click Add. What that's going to do is it's going to add a number 10 down here. And a percentile is sort of what we learned in the past. We learned what is the point where 10% of scores are below. So there's a certain z-score where only 10% of the scores are below that. Then once you add that 10 that you put in there, typing in 10 and clicking Add, put in 20 as a percentile and add that. And so you'll see a 20 appear like I have here. And once you've added that, what that point is whatever score where 20% of the scores are below that. And then what I want you to do is add a third percentile, which you'll put in 30 here and then click Add. And then what it'll do is give us whatever score where 30% of the scores are below that score. So I want you to continue until you have 40% of scores below, and 50% of scores below, 60% of scores below, 70, 80, and 90% of scores below. So I want you to do that until you're done with 100%. Actually, don't go to 100%, sorry. Just go up to 90. And each of these are going to tell us that the percent of scores below that score. So add all those in. Once you do that, I want you to click on standard deviation. We want to measure that in our descriptive statistics. We want to measure the variance, so click on that. And also it would be nice to know the very smallest score and the very highest score. So click on minimum and maximum. Finally, just for a knowledge of central tendency, mean, median, and mode are always musts in your descriptive statistics. So click on those three. Finally, skewness and kurtosis. Up to this point, we've learned what they are, but not really how to measure them in terms of value. So I want you to click on both of those, and they're going to give us a value in the descriptive statistics that tell us what do those mean? What are we actually measuring here, other than just the shape? So click on both skewness and kurtosis. Once you have everything matching this screen here as far as descriptive statistics, make sure to click Continue. That probably will not come up, so if it does, just click OK. So you should get to this screen right here, and we're not done yet. Make sure that display frequency tables are here. We're going to get a frequency table for each one of these 4 variables. So we're going to get 4 frequency tables, but those should be pretty familiar to you up to this point. Last step before we click OK and get this automatically. Run all this data and just get it for free. I feel like I'm just like getting a handout here. We don't have to do any by hand work. It's great. You should feel that way too. Go to charts. Make sure to click on charts, and we need a histogram of this. So click on the button histogram here and make sure that the show normal curve button is checked. So we want to see not only the histogram of the data, but what's a normal curve on top of that. So click those two and press continue. We are ready to go. We are ready to get all this information, and it's a lot. So once you're ready, click OK. So let's take a look at this data before we go any further. This is great because what we can do is look at all the information we've learned so far in the semester, but make sense of it in terms of what real statistics professionals do. So if you were to get this data, which as you recall is about rent and utilities and car and ages, we want to know the descriptive statistics of our 100 people. So right away you can see the average cost of housing was $1328.45. That's maybe in Los Angeles. That's the average rent price. For utilities, people spend an average of $153 on the average car price and the average age price. So you can see those as they go along. But the median value is a little different than the mean value, not too much. But these are really measures of what's central in our data. So you can see that compared to the mean value, the median is pretty close. And that should be the case. The mean, median, and mode are all close together. Same thing with the mode here. The most frequent housing cost was $1,000, and the most frequent utilities cost was $100. For car it was $200, and for age it was $21. But the mode is not very valuable here, because all of these variables, there could be many different housing costs and many different utilities costs and car costs and ages. So it's not likely that 1,000 will be, like 18 times. It could have just happened twice in our data, and therefore it's the mode. Same thing with age. There could have been 3 21-year-olds as opposed to 20 21-year-olds, and that's why it's the mode. So I think the mean and the median are good estimations of where the middle lies for each of these variables. Now with standard deviation, that's just how many chunks away from the mean your scores are, or how far away you can go from the mean value. And each of these have a standard deviation along with their variance. So the variances, the standard deviation, the mean, median, and mode all look about the same. And these are things you should be familiar with at this point. However, with skewness, you'll notice that's different. We've never measured that with SPSS, and we've never measured kurtosis with SPSS either. So it tells me that we're going to be doing some new stuff, some new calculation. So what I want you to do for now is skip that, and we're going to go to percentiles real quick. Percentiles, as you recall, was a certain number where 10% or 20% or 25 or 30% of the scores were below that value. So as you can see, the 10th percentile, what that is a score where 10% of the data is below that score. And that score for housing was $602.50. That tells me that at a rent of $602.50, only 10% of rents were below that. For this number here, $755, 20% of rents were below that. Same thing here, 25, at a rent price of $850 per month, only 25% of scores were below that. And it goes all the way up to 90th percentile. So the 90th percentile is $2,009. That means that 90% of scores for the housing cost were below this price, meaning this is a pretty expensive price. People in the 90th percentile have a pretty high rent. 90% of scores are below that. I know my rent's below that. So anyway, you can do the same thing for utilities. You can see that the 10th percentile is $88. So only 10% of scores is below $88.10. Whereas to pay $240 some dollars per month on utilities, you'd be in the 90th percentile, meaning 90% of scores are below this cost for utilities. Same thing for the car variable, you can see those percentiles, and the same thing for the age variables, you can see those percentiles. As far as frequency tables are concerned, I don't want to spend too much time on those because you should know those pretty well. As a frequency table, for example, for housing, you can see that only about one time do you see a housing cost of $250. That's not that much per month, so that only occurs one time. Whereas, if you look over here at $850 per month, that occurs 6 times, so it's much more frequent to see a price of $850 per month. And then you can see that $1,000 per month occurs about 7 times. So in this area, you're seeing most of the scores that are the most frequent. Whereas as you get higher or lower, there's less and less scores. Strangely enough, there's a frequency for $1,600 a month that happens 6 times. So that's fairly frequent. And it's away from the middle range of scores. And also you get a frequency table for utilities, you get a frequency table for car costs, and you also get a frequency table for age costs. But sometimes it's a lot better to see these frequency tables as histograms. So SPSS gave us a histogram, very nicely put out here. You can see that for housing, most of the data is occurring in this region. It seems that between somewhere around $1,000 per month is the most frequent data in this set. However, you'll notice that this graph is skewed slightly to the right. There is a really high rent value over here of around $4,000 to $4,500 that doesn't really meet where most of the data is in the central area. So these numbers would possibly be considered outliers. If that's the case, then they would have to be removed from this data set, so we would have a much more normal looking curve. But for now, we're just going to look at this data and sort of analyze it instead of actually crunching any numbers. Same thing for utilities. If you notice, most of the data is occurring here. So about 100 to 150 is where most of the data is occurring for utilities. However, there are some people spending $400, even almost, or $550 per month on utilities. They're either running like an amusement park in their backyard or something that takes a lot of electricity, because to spend that much per month is $550 on utilities. That's crazy. But yes, most of the data for utilities is occurring in this area. If you look at this graph for car costs, you can see that most of the data per month is about $200, and that's the most popular and most frequent scores. However, there are some outliers of people spending $600 roughly on their cars per month. And that might be considered a really too high of an outlier, and it might be skewing this data to the right. Finally, if you look at the age distribution here, you can see that there's a problem. This graph is very spiky, meaning most of the ages are occurring really at the middle value here. And that's a problem because we don't want everybody to be a certain age. But what do you notice about this? It goes from an age of 0 to 50, and then there's someone who's age 200. That doesn't make any sense. So what I want you to do is go back to your data set and find that person who is 200, because clearly that's an impossible score. So go back to your data set and we'll search through the ages. I'm going to see who's 200 years old. So scroll down, oh my god, it was this person. 200 years old? That's crazy. So what we want to do is get rid of that, because we don't really want that person in our data. If they're 200 years old, that means they're just some sort of like ancient mummy or something. I don't know, but just get rid of it. So click on the number for that person. It should highlight the whole row. Right click and clear them from your data set. We do not want to include them in our data. So if we get rid of them from our data set, what I want you to do is now find another histogram for age so that we can see what happens to the graph. Keep in mind that this was our graph for age, but it's really, really weird looking. It's too spiky and kurtotic because there was a 200-year-old in there. So go ahead and run a new histogram for this data. Click on Analyze, Descriptive Statistics, and Frequencies. So we only want to run that for age. So take out these three, highlight these three, and click the arrow over. All we're going to be doing is running a histogram for age. So when you're ready, click OK. Everything should be set for you. And what you'll do is you'll come up with a few statistics, but it's only for age. We're not really interested in this table as of yet, because that's kind of what we saw before in the previous table. So click on this table and you can press delete. And you can click on this table here for frequencies and press delete. It'll get rid of it. What we were interested in is this graph. So what do you notice between this graph and this graph? This one is very skewed to the right, to positively skewed because of that outlier. But when we have the outlier removed, what happens to the data? It looks much more normal and fits most of the data in our center. So that is really valuable to see in SPSS. When you remove an outlier, your data becomes much more manageable. Alright, so finally, what I want you to do is scroll up a bit. We did not talk, if you go back all the way up, we did not talk about what skewness and kurtosis was. So that takes a little bit of investigation here. In order to get an overall view of whether there's an outlier in your data set, you need to look at your skewness value and your kurtosis value. So what skewness does is, I'm not going to go into the details, but SPSS analyzes your data and sees if there's a certain skewness from what the mean is. And based on that number, you can take it and compare it with the standard error of skewness. And that's something we talked about 2 lectures ago. So the standard error of skewness and skewness go hand in hand. So for our first housing variable, you notice that the skewness was about 1.993. That's approximately how many standard deviations our variable is skewed. But in order to get a real picture of what the skewness is, you need to take this skewness value of 1.993, and divide it by the standard error of skewness. So we're going to take 1.993 and divide it by our standard error. If you have a calculator handy, you can plug that in, 1.993, and divide it by the standard error, 0.241. So what you want to do is, once you have that information plugged into your calculator, see what it is. Usually a normal skewness value will be no more than 3.3. or if it's in the negatives, it will be negative 3.3. So skewness is normal between negative 3.3 and positive 3.3. What do you notice about our skewness calculation? It's 8.26. That just means it's a very, very high skewed in the positive direction. If this was a negative 8.26, it would be very, very skewed in a negative direction. So skewness, dividing this number, skewness, by the standard error of skewness, gives you an overall picture of how skewed your data is, roughly in standard deviations. And this is not good. This means that you have a really, really high value somewhere in your data. You probably need to get rid of it. But for now, we're going to go on to utilities, just to see how to calculate the other skewness value. So for utilities, we can see that the data is skewed about 1.68 standard deviations. Now that's positive, so it's skewed in a positive direction. But in order to figure out what the overall skewness is, we need to take this number for skewness and divide it by the standard error of skewness. So take 1.68 and divide it by 0.241. And we get an overall skewness for utilities variable of 6.97. So again, very highly positively skewed. You can do this for car and for age, but you're all going to get numbers greater than 3.3. If these were negative values, you would get numbers less than negative 3.3. So when you do these calculations, look for about 3.3 as your cutoff for whether or not there's a skewed variable. If it's greater or beyond 3.3, if it's more than 3.3 or less than negative 3.3, that just means that there's probably an outlier in your data. Just to show you that example, remember age, where there was a person who was 199 years old in our data set? Look at the skewness value for that data set. 7.155. That's huge. That means there's some number in your data set that's 7 standard deviations beyond the mean value. If we take the skewness value and divide it by the standard error of skewness here, you can clearly see that there's some data that's in our set that is way, way beyond the mean. And so anything greater than 3.3 is going to tell us that. It's your job after you find this is too large to go into the data set and delete, which is what we did. So with kurtosis, you can do the same exact process. Kurtosis, as you recall, can either be high or low. High kurtosis is what we got when we did this. This was a really high kurtosis graph. So in our data set, if you take the kurtosis value, which is how grouped data is around the mean, and you divide that number, that kurtosis measurement, by the standard error of kurtosis, which is this number, you take that divided by that, you can get an overall estimation of how kurtotic, or how much kurtosis is in your data set. So let's try that. 5.472 divided by 0.478. And when we do that, we get an overall kurtosis evaluation of 11.44. Just like with skewness, anything over 3.3 is too kurtotic, meaning there's too much kurtosis. And that's probably because most of your scores are too close to the mean. So when you get when a really, really high number, and that's over 3.3, it tells you that most of your scores are too close to the mean. And that's high kurtosis. If this value right here was negative, that means you would get a value of negative 11.4476. And that tells me that the kurtosis is too low. And if you, as you recall, low kurtosis is that really flat graph. Looks like it's smushed down. And that's when scores are too spread out from the mean. You can do the same thing with the other scores. You can take, for utilities cost, you can take 5.812 as an overall kurtosis measurement and divide it by the standard error of kurtosis, but you're going to get a similarly really, really high kurtosis value. If you'll notice our graph for age, when there was an outlier in the data of 199, look how high the kurtosis is for age. That's because there was an extremely high outlier in our data set, and that tells me that our data is mostly grouped around the mean, but that one high age, 199 years, brought that kurtosis really high, because if you look, most of the scores are grouped around the mean. The reason that is because there's one score screwing up all the rest of the data. So when we remove that score, what should happen is this. Our graph looks much more centered towards where the middle is, and the kurtosis is way down because not everything is grouped in the mean right here. There's scores that are spread out from the mean as well. This descriptive table, most of these graphs are skewed, and most of these graphs have way too high kurtosis because there were outliers in this data. As you recall from the histograms, for housing, here's a possible outlier. That's going to bring the number one, the skewness, and the kurtosis up. Same thing over here for utilities. We have a couple outliers over here. What that's going to do is bring the kurtosis and the skewness up. Same thing with car. There are a few outliers over here, so it's going to bring the kurtosis and skewness up. Same thing with age. So in general, looking at this data here, you should be able to get this data from SPSS, take a look at it, and be able to figure out what your overall set of information and numbers is. The good center area, how skewed it is, how kurtotic it is, how spread out it is, and split the data into certain percentiles or quartiles so that you're able to figure out what's a high value, what's a low value, and what's normal for this data. And that's the whole point of figuring out any descriptive statistics. Alright, so finally for this data I want to show you one last thing before we end. It's a box plot. Up to this point you may have heard of a box plot, you may have even seen a box plot. I don't know, you may have a box plot tattooed on your arm. I don't know if anyone has seen box plots yet, but this is my job, is to introduce you to it. Because a lot of the times when you're reading any statistics on any data, a good picture like a histogram is a box plot, and a lot of times they'll report that, the researchers or companies, about their data. So go to graphs in SPSS. Once you're here, go to graphs and go to chart builder. If you'll notice, there is a few choices down here. We can set up a bar graph, we can set up a line graph, a histogram we could also do. But I want you to do a box plot. So take box plot, see this picture that appears right here, or if I click on it, it usually will say it's a simple box plot. So take that and drag it, actually drag it up here into this window, which will be empty for you. Once you drag this into this window, you'll see this kind of setup up here. And what it's asking us to do is put our score that we want in either the y-axis or the x-axis. So what I've done is I've chose housing. You can either put it in the y-axis or the x-axis. But what I would do is just put it in the y-axis for now. And so take housing and drag it over here until you see this axis kind of light up. So let go, and you should see a little bit of change occur over here. This is good because now it's telling SPSS we want a box plot for housing, and I'll explain what a box plot does and how to read it. So once you do that, that's all you got to do. Click OK. And so what you should get is a box plot that looks like this for the housing variable. What's really cool about this is it tells you everything that we learned today, more or less, in one simple graph. So right away you see a little box, hence the name box plot. Sometimes it's called a box and whisker plot. This is a whisker, like a cat. I don't know why somebody had to make an animal out of this box plot, but I guess that's what we do as people. We make little cute names for statistical charts that can sometimes be boring. But this box right here in the box plot has to do with your interquartile range. So right away you can tell that the highest part of our interquartile range is Q3, and that occurs at this point, at the highest most point of your box plot. That number exactly is at Q3, which if we wanted to line up all the numbers in order and find Q3, we could, but I'm not going to do this. Right away I can just tell you that Q3, for our sake, is at 75%, so at $1,600 for housing. So in our box plot, this number is about $1,600 for Q3. The lowest point of this box is Q1. So this box does tell us from Q3 to Q1 what our interquartile range is. And that bottom 25% is about, somewhere close to 1,000. In fact, I could tell you exactly by looking here, the bottom 25% ends at $850. That's at the 25th percentile. So Q1 at the bottom 25% is $850. So our interquartile range is from here, which is $1,600, to $850. The line in the middle of the box plot is our median value. Recall that when we're dealing with an interquartile range, we are not really using the mean so much. We're interested in the median. So this line in the middle of our box, and our box plot, is the median value, which is exactly 1,000. And if you look back up the descriptive statistics, the median is, actually it's 1,075. So the median value is $1,075. And that's this line right here. Okay, the rest of this box plot is interesting. The whiskers are how far your data spreads out. So this line going up from the interquartile range goes up to the highest number that is not an outlier. So this number right here should be roughly like $2,800, maybe $2,700. But based on the estimation for outliers, it gives us the limit to what's normal, a normal range of our data. So right here is where it kind of cuts off, where things are still not outliers. They're still within the normal range. The other whisker, as you can't really see, is on the bottom here, which is the cutoff for what the lowest point is that's not considered an outlier. Now, actually, $0 is still not considered an outlier. So the lowest point that's still within the normal range is at the bottom here at $0. However, these numbers up here are questionable numbers because they're outside of our whisker, which is the range for normal data. Coincidentally, this is the end of our quartiles, and this is also the beginning of our quartiles. So if you review, this is the beginning of the quartile, and this is the very end of the quartiles when we split our data into 4 categories. However, beyond that are a few points that are just too high for the housing graph. So you'll see a little 8 next to this circle. This circle means that this number is potentially an outlier, and that's person number 8, participant number 8. So let's look at participant 8 and see what their housing cost was. You can see it's around 3,000, but that's really just an illustration. We want to see exactly what their housing cost was, so you know whether it's an outlier or not. So go back to your data, and you can see that participant number 8, their housing cost was $3,000 exactly. And that, for this case, would be considered an outlier in our box plot, which is this number right here. These stars up here, right here, that says 52 next to it, and a star that says 18 and 43, these are the participant numbers for extreme values. So not just outliers, but extreme values that are extremely beyond the interquartile range and the range of data that's normal. This 52 here is person number 52, and they had a housing cost of around $4,000. That's an extreme value. Person 18 and person 43 in our data set had a housing cost of around $4,600. So these two stars here are extremely high values that are not anywhere near the range, whereas person 8 is somewhat close to our normal range of data, but still would be considered a potential outlier. Okay, so that kind of ends it today for learning about quartiles, interquartile range, how to find outliers using that, also percentiles, skewness and kurtosis, as well as box plot graphs. And so now you've learned pretty much everything that we're going to need to continue on during the semester. What I need for you to do in your homework is to copy and paste every chart and table that you got here. So that includes the overall statistics graph that we did. I want you to copy and paste that to your lab assignment. I also want you to copy and paste 1, 2, 3, and 4 frequency tables. Those are for all 4 of our variables. And I also want you to copy 1, 2, 3, and 4 histograms that we got. Actually, there's one more histogram. This was a 5th histogram I want you to copy. This was the one where we removed the 199-year-old. And finally, I want you to copy and paste the box plot that we got. These are all going to be considered for your lab grade. And if you have any questions on how to set this up, you're not getting the data that you should be getting, and you're worried sick, you can email me, and I will be more than happy to walk you through it to where you get the correct answers. Anyway, have a great rest of the week, and I will see you at next lecture, and we'll be starting something completely new. All right, adios, and have a good one.